So I want to move on now to section 3.8. As a reminder, we already did 3.7. That was the chain rule. So we've already picked that one up. And we're moving on to 3.8 to learn the technique of implicit differentiation. And this is going to be a powerful technique for working with more complicated functions or more complicated even equations. So, let's take a look here. So if a function is in the form y equals f of x, then we're going to say that that function is in implicit form, or excuse me, explicit form. Okay. Explicit form. An equation not in that form could still be thought of as an implicitly defined function of y in terms of the variable x. Okay, so we're going to introduce this vocabulary here. Explicit functions versus implicit functions. Okay? So here I've got an equation, y equals 2/3 x minus 5. This explicitly defines y as a function of x. And it's for that reason, even though you had studied equations for a long time prior to learning function notation, that when you were given an equation in this form, then when you started talking about functions, they said, oh, just think of f of x as y. Well, that's not, I mean, there's more to a function than just saying f of x is the same as y. But if your equation was explicitly defining y as a function of x, then the two are interchangeable. Okay? But only when it's in that case. Okay? So in a different form, here I've got the exact same equation in a different form. Now, this is not an explicit function. Okay? Instead, it could be thought to implicitly define a function of y in terms of x. Now, in calling y the thing that's being defined in terms of x, we're making a choice here, and that choice is the common choice that we let x be the independent variable and y be the dependent variable. But technically, when it's in this implicit form, it's not clear who depends on whom. That's why I'm saying it could be thought of, as opposed to is an implicitly defined function. It just depends on your perspective. Okay? So in the previous example, I'm saying that 2x minus 3y implicitly defines y as a function of x. How could we put this into explicit form? We could do so simply by solving this equation for y. So we get, minus 3y equals negative 2x plus 15, or that y is equal to 2/3 x minus 5. And now you see that we have the same explicitly defined function that we had before. Okay. Why are we doing this? Well, in a minute here, we'll talk some more about some of the concrete benefits. But just to give you a heads up where we're going, we want to go ahead and take the derivative of an implicitly defined function. We're going to learn how to take the derivative of this when it's in implicit form as opposed to explicit form. And we'll see why that's beneficial here in just a minute. Okay, but that's where we're going. I want to take the derivative of this expression, this initial expression here, even though I already know how to take the derivative of its explicit form. Okay? All right, so let me give you some context for why we want to do this. Okay? This equation right here could be thought of as an implicitly defined function of y in terms of the variable x. Okay? When I go to try to put this into explicit form, I can't. I can't put this in explicit form of just a single function. Let's see what happens when we try to go ahead and solve it for y. We get x squared plus y squared equals 25. So that gives me y squared equals 25 minus x squared. And what's my next step in solving for y? Thomas, what do you want to do?
Well, to get rid of the square, you can take the square root.
Okay. So Thomas is saying take the square root of both sides. In practice, I don't disagree with that. I would like you to start kind of shifting away from the idea of taking the square root of both sides. You can't technically take the square root of both sides of an equation. Instead, what you're doing is you're applying the square root method, which looks like exactly what Thomas said. When you apply the square root method, you get 25 minus x squared, and we're going to put an x squared here. But what's the part that everyone forgets about when they apply the square root method? We got to have that plus or minus there. And for that reason, we're not taking the square root of both sides. We're applying the square root method. Okay? So what are our two functions? Our first function is y1 equals the square root of 25 minus x squared. And our second function is y2 equals negative square root of 25 minus x squared. Okay? Notice that this expression right here is not a function, let me just say not an explicit function. How come? Why is that not an explicit function?
Because it has multiple solutions for y.
Yeah, the definition of a function is for one given input, the definition of an explicit function is for one given input, there is one given output. But if I were to plug in, say, 0 for x, what are my outputs? Both 5 and negative 5. So that is not an explicitly defined function. In terms of vocabulary you've used before, it fails the vertical line test. That's okay. We can get around it, and that's what we're going to do from here on out. So I still want you to remember what denotes an explicit function, and it must pass the vertical line test. But now we can go ahead and say this is still a function. This expression right here is still a function, y given in terms of x. But I have to, if I want to give it an explicit form, I have to list two functions to describe it. Okay? By the way, what does the graph of this look like? What does the graph of y1 look like? Do you remember?
Semicircle?
The top half of a semicircle, or well, the top semicircle of a circle, right? Yeah, and the negative is the bottom semicircle, and put the two together, what do you have? The circle described by this implicitly defined function. Okay? We'll look at that graph here in just a second. So we can now easily take the derivatives of these two functions. We would say that y1 prime would be what? What's the derivative of y1? Yeah, 1 over 2 times the square root of that expression. Am I done? No, what do I need to do?
Chain rule.
The chain rule, which says take the derivative of what's inside that expression. What's the derivative of what's inside that expression? Yeah, I'll go ahead and write 0 minus 2x, just to remind you, because we haven't done a chain rule since Monday. Okay. Any questions on that? Okay. And so then what is y2 prime? It would be positive 2x. Oops, let's clean these up. I'm going to clean this first one up. This would give me a negative x in the numerator, because the 2's cancel, so we'd have negative x over the square root of 25 minus x squared, right? When we go ahead and clean that up. And when we take the derivative of the second y2, in this case we would just get positive x over the square root of 25 minus x squared. How come positive? Because we had a negative in the original function, and then when we did the chain rule, we'd introduce another negative, and the two would cancel out. Any questions on that, folks? Okay, so we've seen, should you want, if you're given an implicitly defined function, you could try to solve it explicitly for one or more explicitly defined functions, and then take the derivative of each explicitly defined function. Of course, that means you have to take multiple derivatives, right? But what we could see is that even though, so I would say that number 4 was easy to put into explicit form. Number 5, not too bad, but when we put it in explicit form, we had two separate functions. Okay? Number 7 here, this is called the Folium of Decartes. We've got x cubed plus y cubed equals 6xy. Descartes, not Descartes, excuse me. Folium of Decartes. When we put this, you could put this into explicit form. It would require, I believe, 3 separate functions to put it into explicit form, and it would be a lot of work to get it there. Okay? I'm not going to try. I couldn't do it. It would take me the rest of the afternoon to put this into explicit form. You could do it, but it'd be really tough. Okay? Further, I can give you other functions where it's impossible to put it into explicit form. It cannot be done. Nonetheless, I would still like to be able to take the derivatives of these functions, because all of these have graphs, and all of them then would have tangent lines, and on all of them I'd like to be able to talk about the slopes of the tangent lines. So I still want to take the derivative of these implicitly defined functions. The process of doing that is called implicit differentiation.